Okay, here we go. So, oh, that's not hard enough. Here's a harder one. No.
Oh my.
Well, now, just because I want to show you what a great strategy this is, how it turns hard problems into easy problems. That was going to be not dramatic enough. Oh, this one is. Okay, how's that sound to you? Real bad, I would think, right?
Are you being serious?
I'm being serious. That would look real bad, right? What would the rules be associated with doing that? Just makes me tremble just thinking about it. Okay, I would have a quotient rule involving a chain rule and, a product rule and a chain rule, right, in the derivatives. That would be a pretty ugly derivative. It would be lots and lots and lots of writing, right? I mean, it would take a page to do, at least, right? Lots of factoring and writing, and it'd be a mess. Wouldn't it be nice if there were a better way to do this?
Yeah.
Okay. Can you think of a way, now we've talked about this, what's one of the huge advantages of logs? When I take a log of a complicated, remember, think about this in terms of the ladder, the hierarchy of difficulty, right? You got adding, subtracting at the bottom, multiplying, dividing, next rung up, exponentiating, right? One of the big advantages of the properties of logs is they move everything down a rung. This would be a lot easier if we weren't doing products and quotients and powers. If we were just doing sums and differences, those are really easy to differentiate, right? So, can you see that taking a log of the right side would be pretty advantageous? Right, everybody get that? So, let's just look at what happens. If we have to log both sides, unfortunately, right? Because you can't, you have to treat both sides of an equation equally. But if I take the log of both sides, I end up with log y, natural log y, equals the log of all that stuff. But now let's think of all our properties of logs here. How could we simplify that logarithm using these properties? Tell me one thing we could do.
Natural log of x plus the natural log of x minus 1.
Okay, so we could take the product on the top, right? So this part up here, we could rewrite as the sum of the log of x plus the log of all that stuff. What else could we do to that second log?
We could take the tree house up at the top and go down front, so natural log of x minus 1, all of that subtracted by the natural log of the square root of x minus 1.
Okay, and then the bottom,
Natural log of 1/2. 1 half.
when we divide, if we're taking a log of a quotient, we just subtract the log. That's the difference of a log. So we're going to subtract away the log of the bottom, and that's actually to a 1/2 power, so we could bring the exponent out front. So now you can see why we practice properties of logs so much, right? So that looks a lot better, right? Now we can just differentiate that term by term, and that's pretty simple stuff, right? So we have to implicitly differentiate though, because now notice that the y is no longer by itself, it's inside a function, but we practice that, we're good at that. So if we differentiate the left side, what's the derivative with respect to x of the log of y?
Natural log of y times y prime.
No.
1 over.
So what's the derivative, Joe, what's the derivative of log hand? Time, you're right, 1 over hand, good, so 1 over hand. So I'm going to get my 1 over y times pan prime, right, y prime. Well, the y prime just goes on top then. And then all we have to do is just differentiate these term by term. So Maisie, what's the derivative of log x? Easy, right? We got the 3/2 out front. What's the derivative of log x minus 1? Times by 1, right? So it's just 1 over x minus 1 minus 1/2. What's the derivative of log x plus 1?
1 over x plus 1.
So that's pretty simple. All we have to do is isolate y prime. But what's the only thing we have to do to get the y prime by itself? Multiply by y, and this is y. Right? So our answer might look kind of ugly, but who cares? It was really easy to get, wasn't it? Right? So then when we finally, all the dust settles here, we've just got y prime equals y, which is that stuff, times
It's x plus 1.
plus 1 on the bottom, times all that, right? We're just multiplying the whole right side by y, which is that. I wouldn't have to, really wouldn't need to, let's write those better. Like that, right? There's our answer. Do we have to simplify that? I mean, you could, right? If you were to simplify this, if you wanted to add up all these fractions, this gets a little bit tougher. At some point, that might be necessary to do, because we might need to know, as we move into kind of the next stuff that we're going to look at, we're going to need to be able to find the zeros of the derivative, and we need to be able to find all the places where the denominator is 0 but the numerator is not. So at some point, we might actually have to simplify that whole sum up there. But for now, we're not going to, right? Because that's really not part of the derivative process. That's part of the using the derivative process, which we're not doing here. Okay. Make sense? A lot easier though, right? That would have been a pretty ugly problem if we didn't use that trick. So all this really amounts to, this logarithmic differentiation, is if you see a function that's just some convoluted mess of products and quotients and powers, then that's a good candidate for logarithmic differentiation. Okay, would it be helpful here?
No, because it would just be easier to use each and also we would take a lot of course.
Well, I mean, you could. You could. We could. This part right here, we could actually make a little bit easier by using a natural log. But the natural log of a difference, there's nowhere to go. There's no property for the natural log of a difference, right? We know really well that if we do something like the natural log of A times B, yeah, that's helpful. I get natural log A plus natural log B. But the natural log of A plus B or A minus B is simply the natural log of A plus B. The derivative just makes it more complicated here, or the log just makes it more complicated. It doesn't do any good. You see the difference though. The real problem was that. That's a good candidate because all the stuff is being multiplied and divided and exponentiated. Perfect. But if you start to string together different terms, then logarithmic differentiation really doesn't do any good. Okay, it just makes it harder. Okay? Let's maybe try, maybe one more, just a little different look. And then be prepared to turn me loose on this and just practice. What about, makes things easier, but what if we decide we don't even want to use logarithmic differentiation? Could I do that problem? Yeah. What's the rule that applies? Chain rule, okay. But at the outer level, what have I got? I've got something, but I don't have something. Our power rule doesn't allow for a variable in the exponent, does it? It only allows for a constant in the exponent. So we don't even have a rule to do this. And there, if you looked in a big book of derivatives, you would maybe see some kind of a general rule for that, but it's a mess. You never want to ever remember. What you do instead is what? Logarithmic differentiation. It's an easy candidate. Look, it's very compact. You've got an exponentiation process going on here, so unlock that with the log. If we log both sides, what's that equal to? If I use my properties of logs?
2. Natural log of x, what that times the natural log of 2x.
No. Just the 2x comes down, right? The exponent comes down. So we get 2x log x. That's pretty doable.
Yeah,
Right.
that's like this too.
No, I'm not doing 2x to the log x. Think about the rule here. Remember what our property of logs is. The natural log of a to the n is equal to n times natural log a, right? So it's a product. 2x times log x. I mean if you might be looking ahead a little bit, and you're close if you are. There's another term there. So now let's differentiate that. If I differentiate both sides, what am I going to get on the right side? Every time. Y prime over y equals, I've got a product there, don't I? Let's just go ahead and absorb the 2 into the first factor, call it part of u. You don't have to worry about factoring and redistributing. So what do I get? 2x, well, let's think of it this way. It's 2x, so that's my u, right? And that's my v. Okay, u times v prime. What's the derivative of log x? Okay. Plus v times the derivative of u. Right, and so we just end up with y prime equals y times whatever I get when I simplify all that. Well, look, the x is canceled, so I just get 2 plus 2 log x, and then y, we already know what that is. Y is just x to the 2x. Oops. And, you know, probably what you'd really do there is just distribute, wouldn't you? Yeah. So we just write that 2 times y plus 2. If I just distribute the y in both terms, you probably just write all that. Doesn't matter. So derivative. Okay, make sense? Go. I think there's like 6 or 7 problems on this side. They're good. I picked them carefully though. They're good ones. If you can do them, you know it.